Hey calculus students, so you've already learned a lot about antiderivatives and how they're related to integrals, and then rules about how to find antiderivatives. So one common use for antiderivatives is to solve what are called differential equations. So a differential equation is kind of what it sounds like. Differential, do you hear the word derivative? So a differential equation is an equation that has a derivative in it. And so solving a differential equation means solving for the original function. So a differential equation is one that has had the derivative taken, and then solving it means going back and finding the original function. And so when you find what's called the general solution, we've heard this word, that involves adding plus c. And then the particular solution uses the initial condition to find a specific value of plus c. So the steps are kind of in there, right, in the title. But for those of you who like steps, here are some simple steps for solving differential equations. So we're going to use the antiderivative. Use the antiderivative to find the general OG equation. So using the antiderivative to find the general OG equation, the original equation. And then if we want to find a particular solution, we're going to plug in the initial condition, and I will show you what that is. Initial condition to solve for c. Okay. And so let's just jump into some examples of what this looks like. All right. So example 3, we have to solve this differential equation. I know that it's a differential equation because it involves a derivative. And then right here is the initial condition. So it's telling me in my original function, in my OG equation, f, right, there's my f. I know that when I plug in the point 2, I get out -3. So it's basically giving me the coordinate point to -3. That's my initial condition. Okay, so I'm going to follow those 2 steps. So step 1, find the OG equation. Find the original equation. Okay, so I'm going to use the antiderivative. The notation will be f. So the antiderivative of 3x squared, I'll add 1 to the exponent and then divide by 3. So since I already had 3 before, I'm kind of doing that, plus c. And so this simplifies to just x cubed plus c. So this is what is my general equation. There's my general equation. And it did ask, it said find the general, but it also wants my particular equation. And so step 2 is where I do that step. Let's change colors. So I'll also erase that. So changing to purple, now I'm going to find my particular equation in purple. So to do that, I'm going to use the initial condition to solve for c. Okay. So what my initial condition tells me is that at the point 2, -3 means I can plug those points into my f. So my f is x cubed plus c. If I plug in 2, I get 2 cubed. Oh, I'm doing the totally wrong equation. Sorry, let's go back a little. Did any of you catch my mistake? I totally missed out on this +1. I was ignoring this +1 so hard. And so my equation, I need to update it. Good job if you caught me. That means that you understand antiderivatives well. So if you caught me, you're good. But this plus 1, I need to account for that. The antiderivative of plus 1 is x. So both of these I just need to add x, but I still have my plus c. So it's not a big deal. I just don't want to forget that. So then over here, plugging in 2 into those equations. So I get 2 cubed plus 2 plus c. So I plugged in 2, and when I plug in 2 into f, it equals -3. So that's how I use my initial condition, so that I no longer have an x variable, and the only thing I don't know is c. So now I can solve this out. So 8 plus 2 plus c equals -3. 10 plus c equals -3. So c equals -13. Woohoo! I found my plus c, and now I'm going to plug that into my general equation to write my particular equation. So my particular solution is going to be f of x equals x cubed plus x minus 13. There it is. So I have both my general solution and my particular solution. Okay. We're going to do the same exact thing in example 4. So here's my differential equation. It's a differential equation because it has a derivative, and then here is my initial condition. Initial condition. It's running away from me. Initial condition, and this is the coordinate point 0, -2. Alright, so let's start with our step 1 of finding the original function. So using antiderivatives to find the original function. So I'm going to start off by rewriting y prime into something that looks more like one of my antiderivative rules. So this one is kind of a tricky one. It's a very specific antiderivative rule, but if we look back at our table, so if you ever get stuck, use your table. Sometimes I use it too. It looks like this guy right there. So 1 over 1 plus x squared, I just have an extra 20. And so that is the antiderivative. The antiderivative is inverse tangent. Oh my gosh. So it's making us use an inverse tangent. That's pretty tricky. But use your table when you need help. It's okay. So now coming back here, finding my antiderivative will be, oops, not y prime. The antiderivative is just y. The antiderivative of e to the x is e to the x. That one's nice. And then 20 inverse tangent of x plus c. So there's my general solution. And then I'm going to use my initial condition to solve for what c is. So step 2, I'm going to use the fact that at 0 we get -2. So I'm going to plug in 0 into my equation. So I get e to the 0 plus 20 inverse tangent of 0 plus c is equal to -2. Okay. This problem is just torturing us. So we have to figure out what is inverse tangent of 0. So remember, inverse trig functions, this is giving you like the coordinate value, and we have to figure out the angle. So the angle in inverse tangent where tangent will equal 0. And so the angle for which this happens at, review inverse tangent if you don't remember this, but this happens at angle 0. So at 0, basically tangent of 0 is equal to 0. So that solves that. So e to the 0 power is 1. Here, inverse tangent of 0 is 0, plus c equals -2. And now I can solve for c. I get c equals -3. And I plug that into my equation, my general equation, to get f of x. Or was that what it was? It was y. So let's call it by its proper name. Y equals e to the x plus 20 inverse tangent of x minus 3. There is my particular solution with a specific value of c. Okay. Okay, and example 5 kind of brings the challenge up a little bit on the differential equations. And the reason why is because it wants us to now solve a differential equation that involves the second derivative. And it wants us to be able to find both y prime and the original function y. So essentially we're solving two differential equations. And these kind of, they give you different information. So in A, it gives you y prime. Well, these are your initial conditions, right? So A is a little bit different than B. Let's just attack A for right now. So first, we're still going to follow our same steps. I'll turn to green in case you care about my color coding as much as I do. Where I'll start, let's just call this y double prime. I'm going to start by finding the original function. So I'll take the antiderivative to find y prime. So the antiderivative, my exponent would go up to 3. And then I would divide 12 by 3 to get 4. So 4x cubed is the antiderivative of 12x squared. And then the antiderivative of 6x is going to be 3x squared. And then minus 4x plus c. So if you're not sure about that antiderivative, go ahead and check it by finding the derivative to prove that it's correct. And now we're going to be using this initial condition. So at 1, 3, I can plug this into y prime, my y prime to solve for c. So I'll have 4 times 1 cubed plus 3 times 1 squared minus 4 times 1 plus c is equal to 3. So doing a little bit of mental math, I would solve this and get c equals 0. Oh, that's great. So c equals 0. That's fine. So I have y prime equals 4x cubed plus 3x squared minus 4x plus 0 is my specific equation. So I found a specific equation for y prime. Okay. And right here is where I used my initial condition. I don't want you to forget that. So I used my initial condition, and then here is my specific equation for y prime. But I want to go further. I want to find the real particular solution, so that means finding y. So I need to do the same steps that I just did again. So the antiderivative of y prime is going to be x to the 4th plus x cubed minus 2x squared, and then plus c. So I have another plus c that I need to solve for, now using my other initial condition. So this initial condition is for y, which I have now. And so I'll switch back to purple when I plug in my initial condition. So at 0, -6, I really should have done this step in purple too if I were good at color coding. But at 0, -6, I will get 0 to the 4th power plus 0 cubed minus 2 times 0 squared plus c equals -6. So c equals -6. So I found my c that I can plug in to y to find my specific solution. So y equals x to the 4th power plus x cubed minus 2x squared minus 6. And there is my particular solution to the differential equation. Cool. And so B is just a little bit different. You can see in A I got initial conditions for y prime. In this case, I just have initial conditions both in terms of y. So it's going to make the steps that I take a little bit different. Still very similar. So I'm going to start off by finding the general solution, which I already found over here, so I can just write that. So y prime equals 4x cubed plus 3x squared minus 4x plus c. But this time I don't have an initial condition for y prime, so I'm unable to solve for c. So I just have to proceed by taking the antiderivative again. So taking the antiderivative here, I'll get x to the fourth plus x cubed minus 2x squared, similar to what I got before. But now I have to take the antiderivative of c. So this is just a constant, so it's just going to be c times x. And then I need to add another constant. So I'm going to just call this other, this one will be c1, and this other one will be c2. So now I have two values of c in the same equation that I need to solve for. Essentially, it's okay. And the reason why I can solve this is even though I have, so I have two unknown c's, c values. All this means is that we must have two initial conditions, and I do. So I can use the initial conditions one at a time to solve for each value of c. So I'll just plug in this first one here. So I'm plugging in that initial condition. Okay, so I will say at 0, 4, and it's always good when you can plug in one with zeros, because then my x is just 0, right? And that's really easy to calculate. So this one, c times 0, it goes away, and then I have plus my second c, and it equals 4. So everything cancels out, and I get c2 equals 4. So I already know one of my c's. Woohoo! And then I can plug in my other initial condition to figure out c1. So my other initial condition is right here. So it's that the coordinate point 1, 1. So I'm going to plug in 1 for x. 1 cubed minus 2 times 1 squared plus c1 times 1. And then I know my c2 is 4. And this is equal to 1. So doing a little bit of math over here, I get 5 plus c1 equals 1. So c1 equals negative 4. There we go. I have both values of c that I can plug in, just at the very bottom. So now I can write my particular solution, solve for both values of c that I was missing. c1 is minus 4 and c2 is positive 4. So here is my particular solution. So example 5 is a little bit different because we were given the second derivative and we had to go back 2 antiderivatives to find the initial equation.